מה זה הלייטינג טוקס? מעניין. יאללה, אבא תהנה.
תודה רבה. טוב. להתחיל פשוט? יאללה. יש דוברי... תודה רבה. יש דוברי אנגלית בקהל? Cool, so we'll do it in English. Awesome. So welcome everybody to Dependency-Aware Cache Management in Parallel Processing Pipelines. So this might seem like a very large and kind of frightening title, but hopefully by the end of this 15-minute talk, you'll kind of get a bit of a grasp about what this means and where this meets you in your day-to-day work. So before we start, a bit about myself. My name is Aviv, and I'm an engineering team lead at Pecan AI. Self-taught, curious, and also I love memes, which you're going to see throughout this presentation. And I am passionate about software, data, and knowledge, which is why I'm here lecturing at Data TLV. So Pecan AI, a bit about what we do. In 2 words, predictive analytics. But what does that actually mean? So in a bit more words, simplifying the ML process for analysts in the business domain using established well-known tools that analysts know and love. Basically what this means is kind of the world of democratizing AI and ML for analysts using tools that they already know, like SQL, data pipelines, all the things that analysts use on their day-to-day basis. So how do we do this process? Specifically, my team at Pecan, we're responsible for closing the gap between raw data and what we call an ML-ready data set. So basically, most of our customers and also most of the data-driven companies that we have out there have a bunch of raw data. They have maybe transactions and user data and all kinds of different things that things that are collected during the work of the company. And the first step would always be kind of wrangling and reorganizing these data sets into something that can actually be fed into a machine learning model. So I'm assuming that you know at least that if I take just a bunch of tables and I kind of throw them into the magic pot of machine learning, then nothing meaningful is going to happen. So there's a lot of, it's important to kind of structure the data in a way that the algorithm knows how to read and how to use it and produce something that's useful and meaningful and will actually result in value. So after we kind of prepare that data set, we throw it into the magic machine learning oven. And on the other end, we're going to get these dashboards and insights and cool analytics and so on. And as I've said before, the way that we allow you to do this kind of data processing is using simple analyst tools like SQL and defining your pipeline. And that's kind of segue into what I'm going to be talking today, which is, as I said, caching and data pipelines. Just a few kind of leveling out the plane. So a data pipeline, simply put, is just a list or a series of processes that are done one after another. They have a certain input-output kind of relationship. I would like to maybe filter the data. I want to do some aggregations, and so on until the pipeline reaches its end. And we have a mathematical term called DAG, a direct acyclic graph. So a direct acyclic graph is basically a representation of a bunch of nodes and edges. And the rule is only that there has to be a direction between every node, and also that I'm not allowed to make any cyclic references. So C can't be pointing back to A because that would create, a full loop. And hopefully, it makes sense that we would want to model data pipelines using this kind of idea of DAGs, because the same way in data pipelines, my processes are one after another, and also I won't do like cyclic references. I won't be going back to an earlier block in my pipeline. So you might be thinking, okay, so we're doing a bunch of processes. I'm going to do a filter and then an aggregation. So what's the big deal? Like, why are we even talking about this? So enter real life. Just a simple kind of screenshot from kind of benchmark how data pipelines actually look in production in real companies. This is a screenshot from software called Airflow, which is an orchestrator for data pipelines. And as you can see, it's not really as simple as just A, then B, then C. There could be a bunch, maybe hundreds of different kind of processes in this pipeline. They could be doing small loads and heavy loads and using different technologies, maybe Spark, maybe other relational databases. So this whole kind of pipeline thing is very complex, and it's not as simple as just A, B, and then C. So for us as engineers and data engineers, it's important to understand how these things work and then kind of work towards optimizing their performance at the end, resulting at runtime and cost. So if I'm a company and I'm going to be spending a bunch of money on maybe AWS or GCP resources, then my company is going to be losing money, and at the end of the day, the company won't be profitable, so nobody wins. So obviously, it's important for us to understand how to kind of deal with these kind of things. And when we're talking about data pipelines, mostly we're looking at read-write operations, which are kind of the heaviest things, and also compute resources. If I'm going to be scanning a very big table, for instance, that has millions and millions of records, I'm not going to be able to get through that in a timeful manner without wasting a lot of resources. Most engineers, when we talk about performance and optimization, we're going to talk about cache. Cache is like one of the simplest and go-to strategies. And again, just to level the plane, so a bit about what caching is. So if you imagine a retail like a Schufelsaal or whatever store that sells goods, so they have a big storage house where they have all their stock, and it's kind of ordered in these big boxes and stuff like that. But the time it takes to kind of get a soda bottle out of that box would be a long time. I might need a forklift to go like to the second level and take out the whole plate and then kind of extract specific items. And so the company makes smart decisions about what items they want to place in the stores where they're reachable and accessible to the consumers. And then us, the consumers, we kind of just walk into the store and we can easily just grab that bottle of soda. So in this kind of analogy, the store is our caching for the warehouse. So the supermarket is not going to be putting their whole stock in the super because there's no space for everything, and they want to maximize value for once you get into the store, you're going to find your items pretty quickly. And so they're going to choose and curate the list of things that they put easily and accessible to everyone. So most of these mechanisms in the world of caching basically are recency-based, and the most kind of popular algorithm is called LRU, which means least recently used. So let's say I'm on a field trip with some friends, and I have a bag of chips and cookies and maybe a pack of gum. And you know how every time you pull out the gum, so everybody's kind of hoarding around you and like, I want one, I want one, I want one. And so you're going to be, OK, I'm not going to put it back in my backpack because somebody's going to come by and ask for it again. So I'm going to put it here in my pocket. But my pocket is really small. I can't put also my cookies and my chips and all the other stuff. I'm going to leave those in my backpack and only keep the gum here. So I'm making a conscious decision about what to put in my pocket, which is more accessible. But also, it's going to be, I forgot the rest of that sentence, sorry. Anyway, so the strategy that I'm putting in play here is that things that are often requested, things that are popular in demand are going to be kept here in my pockets, while things that I only use once in a while I'm going to keep in my backpack where it takes more time to pull out. And then this kind of strategy is best mostly for small items and also unrelated items. So I can be giving out gum and chips and cookies, and I don't have to serve them together like on the same platter or whatnot. Nobody's going to be eating gum and chips and cookies at the same time together. So I can kind of distinctly decide when I want to put out each one of these items into my so-called cache. But then if we're going into data pipelines, this kind of strategy isn't the best way to go. And the first reason would be the objects that I'm talking about are really large. So a data set could be easily gigabytes or terabytes of data. And it's not something that I can just kind of, OK, let's put some of these in my pockets and walk around with teras or gigabytes of data sets in my pockets as if it's a simple thing to do. And also, in data pipelines, we have relationships. So the different processes are not happening randomly, and I can access each one of these blocks at a random time. They're happening in a certain order. So it's interesting to know when something will be accessed so I can kind of plan ahead and put it in my cache accordingly. So for this, in a paper published in 2017, was introduced something called LRC, which is a different way to use caching, called least reference count. And basically, the idea here is that we look about what processes are referencing the things that I want or need or use, And then I make a conscious decision about if I'm going to put them in the cache or not based on who's going to be needing them soon enough. So a quick simulation. The orange kind of block means that something is cached, and the green means that a block has been calculated. So for the first round around, obviously I'm going to be calculating A, B, and C because they're the earliest in my pipeline. And on the next step, I'm going to be calculating D. And at this point, I can cache D. But then, if you look at the graph, B has nobody referencing it. Nobody that's going to be next in line is going to be using B anytime soon. So I can evict it from my cache. I don't need to keep it in my storage. I can be smart about the options and the decisions I make. So going forward, I'm going to go on and calculate E and F. And then again, also, A, D, and C are now not referenced by any of the uncalculated blocks. So there's no benefit for me kind of keeping them in the cache. And this way, what we end up is kind of minimizing the amount of storage that I need to keep in order to have a kind of performant and working kind of system. And if we're looking a bit about the metrics and kind of benchmarking performance and stuff, so PageRank, if you know, is an algorithm that's very dependency-based. It's talking about if there's a group of people and I want to kind of figure out who's pointing to who, it's most relevant for kind of social networks and stuff. So you can see that if I have a cache size that is the same size of my data set, then it doesn't matter, right? Because I'm in the storage house and everything is accessible to me, so it's the same cost kind of finding any item. It doesn't matter which it is. But now that I'm kind of shrinking the cache and I want to optimize it, we see on the left that the hit count for the LRU-based strategies is a lot worse than for LRC. And in comparison, the runtime for this increases dramatically for LRU-based versus LRC, meaning that every time I need an object and it's not accessible to me in the cache, I need to go back to the storage room and start looking around for it, obviously resulting in longer kind of processing time, longer read-write, and so on. So going back to kind of what's in it for me, as you can understand, looking at the dependencies between the objects that we're using is crucial for optimizing storage and runtime performance. If I'm not understanding that, I might not be leveraging my resources correctly and kind of wasting time and money for everybody using these data pipelines. A short example from our real life, let's say, how we use this. So as I've said earlier, we're giving SQL queries to analysts so they can kind of do the data wrangling and processing on their own. So on the left, you can, it's a bit small, but on the left, you can see that an analyst kind of defined a bunch of SQL queries. And these queries are kind of referencing each other. They're using each other to kind of define the processes in which things are happening. So first step, we're going to do a compiling action where we kind of figure out, we read the SQL and we figure out which of these queries are related to which of the other queries. The next step, the evaluator is going to reach into the cache and look which of these blocks have already been calculated and kind of tag these different blocks and say this one is cached, this one isn't. And then all of that is sent into the optimizer, and the optimizer says, OK, these blocks have been calculated. I don't need them. These blocks are. Might be a small feedback loop about which blocks I want to cache and which blocks I don't. And then only the subset that's relevant that actually needs to be run is what's actually sent into the executor. And of course, going through the caching layer to kind of keep the process going for the next iteration, and so on. So for summary, we've talked about what a pipeline is, what a DAG is, and why we model pipelines as DAGs. The importance of understanding dependency for optimizing resources and performance, dependency-aware caching LRC as a strategy to deal with this issue, and a short example of how we use that in real life. So thank you very much, and hopefully you've learned something.
Yeah. Thank you.